Alright class, we've got one more thing we want to talk about before we finish our discussion as we're getting ready from space curves to getting into leaving space curves, getting into motion in 3-space. And that's this notion of the T, N, and B vectors. And what we're doing is we've got an object moving through space, and we want to create a coordinate system of 3 axes relative to the position of the object moving along the path. T is the unit tangent vector, N is the unit normal vector, and B is the unit binomial vector. And just to kind of get an idea for what these are, here's a nice little YouTube clip animation that will show some of that. I'm going to make it full screen here. And so in this animation, there it goes, here it goes. The unit tangent vector is that red vector. There it goes, now it's moving. The unit tangent vector is that red vector. The blue vector is our unit normal vector, and the green is the unit binomial, the B vector, unit binomial vector. So red in this animation is the unit tangent vector. You can see how it's kind of following along the curve. The blue one is the unit normal vector, and it's kind of on the inside of the curve. Let me go back here a little bit again, and we'll pause it at some point right in there. It looks pretty good. So the unit tangent vector, the red vector down here at the bottom, is moving along the shape of that curve. The unit normal vector is perpendicular to that, but it's pointing sort of inwards, in towards the center of the curve. And then the binomial vector is perpendicular to those two. So we have those 3 vectors. It's sort of creating a frame of reference for objects as they move around this this 3-dimensional space. And I'll post a copy of this into the description of this video so you can get back there and see it later on in the tournament, for reference. If you want to come back and look at it, I'll post a link to it so you can see it too. We've already talked about how to find the unit tangent vector. What we want to do is we want to look at r prime of t. R prime of t gives you a vector that's tangent to a curve, and what we want to do is divide that by the magnitude of r prime of t to turn it into a unit normal vector. That will give us our unit tangent vector. Our unit normal vector, the way we're going to come up with that is a little bit of a nice sort of thing. There's a nice theorem that's out there that says that if the magnitude of r of t, so if you've got some vector valued function and the magnitude is a constant, then r prime of t will be perpendicular or orthogonal to r of t, to the original vector valued function. The derivative, that vector valued function that you get by taking the derivative, will be perpendicular to the one that you started with. And you can get that because we know that the magnitude of r prime of t is just r of t dotted with r of t. Well, actually it's the square root of r of t dotted with r of t. And so that's going to equal our constant. And so what I can do is I can square that. And if I square that, I'll get that r of t dotted with r of t, that's the square of your length, is also equal to a constant. It's a square. In this case it was the original constant squared, but it's still a constant. If you take the derivative then of this thing, if you look at the rate of change of this r of t dotted with r of t, what that is, it's going to be the same as the derivative of c squared, but c squared is a constant, so the derivative of c squared is going to be 0. But the derivative of the dot product, what you can do is you can use the product rule on it. That's going to be the derivative of r of t dt multiplied, or it's going to be r prime of t, multiplied by, or dotted with r of t, plus the first term, r of t, times an r prime of t. And that's the dot product in there. We're talking the dot product, the scalar product in there. And so what we end up with, I'm going to change this notation here. This should just be r prime of t. And so what we get there is we got the same thing. We're going to get 2 times the dot product of r prime of t and r of t. And that's going to give us 0. And if I've got a non-zero vector that I'm starting with, if r of t is non-zero, and I've got the 2 of these that is dot product together and give me 0, that means that r prime and r are perpendicular to each other, right? Because that's the only way you could get a dot product of 0 is if their derivatives are perpendicular. And so what we're going to do to find n is t is a unit tangent vector, and so n is going to be t prime of t. So that makes n and t perpendicular to each other, but t prime isn't necessarily a unit vector, so I also have to divide by the magnitude of t prime of t, because I'm not always guaranteed, even though I'm starting with a unit vector, when you take the derivative of it, you're not guaranteed that you're going to get a unit vector when you're done. And actually, frequently you're not getting a unit vector when you're done. So you have to divide by the magnitude of t prime of t. So that's how we're going to find our unit normal vector. And then our binomial vector, we want something that's perpendicular to both t and n. And we can just get that by doing the cross product. We're just going to take t cross n to get our binomial vector. The b vector is the binomial vector in there. So that's how we find t, n, and b of t. They're a little bit difficult to calculate as well, but there they are. Alright, here's a nice osculating circle. We'll make it full screen here for you. What we have is a parabola. That's the blue parabola, and the black thing is showing the osculating circle, the circle that's kind of tangent to that curve. It's got matching the curvature as you go across there. It's going to bounce up. I think it's going to come back here as it comes through. Yeah, here it comes back again here. And you're actually showing the normal line and the perpendicular line there on this one. And the center of the circle is that dot there as it comes across. So you've got a nice osculating curve. It's just kissing the graph as we go across there. And here is the other one of an osculating circle. This one's a little bit more exciting because it's not just a parabola. It's got a little bit more move to it there, and you can see the osculating curve circle as we move across this curve. It's showing the osculating curve. You'll notice again that the curvature is largest when the circle is smallest. Those two have a reciprocal relationship, but when the curve is curving the most, that's when your curvature is largest. So up here at these corners, like right up here, you're curving really fast and you get a pretty small circle. Out here towards the end, you have a circle with a very large radius. Okay, so there's where it's got a small. We'll come back. Oh, I guess we're done with that there. All right. And that should do it. Let's